Welcome all. Now we are going to discuss about Banach spaces. A normed space X over K is called a Banach space if X is complete in the metric d of xy equal to norm x minus y induced by the norm on capital X. Okay, so every normed space need not be a Banach space. A normed space can be a Banach space if it is complete in the metric induced by the norm on X. Okay. Now we have a result that a subspace Y of a Banach space X is a Banach space if and only if Y is closed in X. Okay, so every subspace of a Banach space need not be a Banach space because a subspace can be a Banach space if and only if it is a closed subspace of capital X. Okay, now we will see the proof. Suppose X is a Banach space and Y is a subspace of X. Assume Y is Banach. We have to prove that Y is closed in capital X. Okay, so Y is Banach means Y is complete in the induced norm. Now we have to prove that Y is closed. For that we have enough to show that for a sequence Yn converges in capital Y, the limit point also in capital Y. Okay, for that choose a sequence Yn in capital Y such that Yn converges to Y in capital X. We have to show that that limit point Y is an element of capital Y. Okay, since the sequence Yn converges, it is clearly a Cauchy sequence in capital Y. Okay, so and since Y is Banach, that Cauchy sequence converges in capital Y because in a Banach space every Cauchy sequence converges. That means the limit point Y is an element of capital Y. Okay, so Y is closed in capital X. So if Y is Banach, then Y is closed in capital X. Conversely, assume that Y is closed in capital X. We have to show that Y is Banach. For that, choose a Cauchy sequence Yn in capital Y. We have to show that it converges in capital Y. Okay. Let Yn be a Cauchy sequence in capital Y means Yn is also a Cauchy sequence in capital X. And since X is Banach, Yn converges to some Y in capital X. Okay. And since Y is closed, that limit point should be an element of Y. That is, Y is an element of capital Y. Means the Cauchy sequence Yn we have selected converges in capital Y. Means capital Y is complete. And so capital Y is a Banach space. Okay, so every closed subspace of a Banach space is a Banach space. Now we are going to see some examples for Banach spaces and non-Banach spaces. Okay, the first one is Kn with any of the norms norm P where 1 less than or equal to P less than or equal to infinity is Banach, because we have seen that Kn is complete in any of the norms norm P, and so Kn is Banach in any of the norms norm P. Okay, and the second example is every finite dimensional normed spaces are Banach spaces. Okay, every finite dimensional normed spaces are Banach spaces. The proof is as follows. Suppose dimension of X is equal to n. Okay, we have to show that X is Banach. By the theorem 6.3 B part, if dimension of X is equal to n, there is a linear homeomorphism from Kn on to capital X. Okay, and we know that Kn is complete in any norm P, and since there is a linear homomorphism from Kn on to X, and since Kn is complete, we get X is complete. Okay, by the theorem 6.3 again. And so every finite dimensional normed spaces are Banach. And the next example is the small LP space for 1 less than or equal to P less than or equal to infinity with the norm P are Banach spaces, because we have seen in the theorem 3.3 that the LP spaces with norm P is complete, and so they are Banach spaces. So the LP spaces, the space of all k-valued p-summable sequences with norm P are Banach spaces. Okay, next we have capital LP of E where 1 less than or equal to P less than or equal to infinity with the norm P where E is a Lebesgue measurable subset of R, are Banach spaces, because in theorem 4.6 we have seen that LP of E with norm P is complete, and so they are all Banach spaces, where LP of E is the set of all equivalent classes of P integrable functions on capital E. Okay. Next we have B of T. The space of all k-valued bounded functions on a set T with submetric is Banach. For that, consider a Cauchy sequence xn in B of T. Then the submetric is actually d infinity. So xn is a Cauchy sequence in B of T, means d infinity of xn xm is less than epsilon for every n and m greater than or equal to some n naught. This means that actually d infinity is norm infinity of xn minus xm. So norm infinity of xn minus xm is less than epsilon for all n greater than or equal to n naught. Okay, so the metric induced by the norm is submetric actually, and the norm is subnorm here. Okay, so this means supremum of all mod xn of t minus xm of t is less than epsilon for all n and m greater than or equal to n naught. If the supremum is less than epsilon, this means every member of the set is less than epsilon. That means modulus of xn of t minus xm of t is less than epsilon for every t element of t and for all n m greater than or equal to n naught. This means that sequence xn of t is a Cauchy sequence in K for each t element of t. And since K is complete, we can say that these sequences converges in capital K. That is, sequence xn of t converges to some x of t in capital K as n tends to infinity. Okay, and we have xn element of B of t, means supremum over t element of t mod xn of t is finite, that is, it is less than infinity for every n. Means supremum over t element of t mod x of t is also less than infinity, because xn of t converges to x of t in K as n tends to infinity, and so the supremum is less than infinity, means x is an element of B of t. And so norm infinity of xn minus x is equal to supremum over t element of t of all mod xn of t minus x of t is converges to 0 as n tends to infinity, means xn converges to x in B of t. Okay, so we have selected a Cauchy sequence in B of t. Now we obtain that Cauchy sequence converges to a point in B of t, means B of t is complete and hence is a Banach space in the subnorm or in the submetric. Okay. Next we have C of t of all k-valued bounded continuous functions on t, where t is symmetric space, is a Banach space. Okay, we have C of t equal to set of all x element of B of t where x is continuous on t. That is the space of all bounded continuous functions on t. Okay, we know that B of t is complete in the submetric. Now consider a sequence xn in C of t such that xn converges to x in B of t. We have to show that B of t is closed. Okay, sorry, we have to show that C of t is closed. For that, consider a sequence xn in C of t such that xn converges to x in B of t. For that, we have to show that x is an element of C of t. Okay, xn converges to x in B of t means d infinity of x in x is less than epsilon for every n greater than or equal to some k dash. Okay, that is supremum over t element of t mod xn of t minus x of t is less than epsilon for every n greater than or equal to k dash. Supremum is less than epsilon means every member is less than epsilon, that is mod xn of t minus x of t is less than epsilon for every n greater than or equal to k dash and for all t element of t. This means that the sequence xn converges to x uniformly on capital T. Okay, now let t naught element of t and epsilon greater than 0. Then since xn converges to x uniformly on t, we can say there exists some n naught such that d infinity of xn naught comma x is less than epsilon by 3. Okay, this is happens because xn converges to x uniformly, and so we can choose n naught such that xn naught d infinity of xn naught comma x is less than epsilon by 3. Okay, and also since xn naught is continuous at the point t naught, we can write modulus of xn naught of t minus xn naught of t naught is less than epsilon by 3 whenever d of t comma t naught is less than delta. then modulus of x of t minus x of t naught is less than or equal to mod x of t minus x naught of t plus mod xn naught of t minus xn naught of t naught plus mod xn naught of t naught minus x of t naught. We are just subtracting and adding some terms, and using the properties of modulus we are splitting this. Okay, and this is less than or equal to d infinity of x xn naught plus epsilon by 3 plus d infinity of xn naught x. Okay, by the equations inequalities we obtained above, and this is less than or equal to epsilon by 3 plus epsilon by 3 plus epsilon by 3, which is equal to epsilon for every t with d of t naught is less than delta. Means that x is continuous at the point t naught. Okay, so since t naught is arbitrary, we get x is continuous at every points of capital T, means x is an element of C of t. Okay, so we have chosen a sequence xn in C of t, and we have found that xn converges to x and x is an element of C of t. Means that C of t is a closed subspace of B of t, where B of t is a Banach space, and hence C of t is become a Banach space in the SUPNA. Okay. Next we have the example C naught naught is not a Banach space when it considered as a subspace of L infinity. Okay, we know that C naught naught is the set of all x element of L infinity such that all but finitely many x of g's are equal to 0. That is, the bounded sequences such that all but finitely many x of g's are equal to 0. Okay, and we know that L infinity is a Banach space, and so L infinity is complete in the norm infinity. But C naught naught as a subset of L infinity, as a subspace of L infinity, is not closed, because if we consider the sequence xn is equal to 1, 1 by 2, 1 by 3, etc., 1 by n, comma 0, 0, 0, etc., is an element of clearly C naught naught. Okay, because the first n terms are non-zero and all other terms are 0. So this sequences are all in element of are all in C naught naught. But we can see that xn converges to the sequence 1, 1 by 2, 1 by 3, etc., which is clearly is not an element of C naught naught. Okay, so C naught naught is not a closed subspace of L infinity, and hence it cannot be a Banach space. Okay, so C naught naught as a subset of as a subspace of L infinity is not a Banach space. Next we have C naught naught as a subset of LP is again not Banach. Okay, as we have seen above, C naught naught is the set of all p summable sequences such that all but finitely many x of g's are equal to 0. Okay, and in this case we can see that C naught naught closure is equal to LP. That is, C naught naught closure is not equal to C naught naught. Okay, because we have seen in the above example that there is a sequence xn in C naught naught such that xn converges to a point not an element of C naught naught, but that point is an element of LP. Okay, and so C naught naught closure is equal to LP, not equal to C naught naught, and so C naught naught is not closed in LP, and hence it is not Banach as a subspace of LP. Next we have C naught as a subspace of L infinity is a Banach space. Okay, we have C naught is equal to set of all x element of L infinity where x of j converges to 0 as j tends to infinity. Means C naught consists of all sequences converges to 0. Okay, in this case we have C naught naught closure is equal to C naught in this case. That means C naught naught closure is equal to C naught in L infinity. Okay, as we considered C naught as a subspace of L infinity, C naught is equal to C naught naught closure. Okay, this means that C naught closure is equal to C naught, and hence C naught is closed in L infinity, and hence it is a Banach space. Next we have C, subset of L infinity is a Banach space, where C is the set of all x element of L infinity where x of g converges in K as j tends to infinity. That is the space of all convergent sequences in L infinity is a Banach space, because here C closure is equal to C, and hence C is closed in L infinity, and so it is Banach. Next we have C of AB as a subspace of LP of AB is not Banach. Okay, for 1 less than or equal to P less than infinity. We have C of AB is equal to the space of all bounded continuous functions on AB, and LP of AB is equal to the space of all equivalent classes of P integrable functions on AB. Okay, here we are considering the norm is norm P of x is equal to integral a to b mod x of t raised to p dm whole power 1 by p. Okay, by theorem 4.7 b part, we can see that C of AB is a proper dense subset of LP of AB. That is, C of AB subset of LP of AB, and C of AB closure is equal to LP of AB. That implies C of AB closure is not equal to C of AB, means C of AB is not closed in LP of AB, and hence it is not Banach. Okay. To see that is not closed in LP of AB, consider the characteristic function on AC, on the closed interval AC, where C is in between A and B, such that chi AC of x is equal to 1 for x element of closed interval AC and 0 otherwise. Okay, then we can clearly see that norm P of this characteristic function is a finite quantity, and so this characteristic function is an element of LP of AB. Okay, that is the C of AB closure, but this characteristic function is not a continuous function, and so it is not an element of C of AB. Okay, so there are functions which are not in C of AB but in the closure of C of AB. Okay, and so we can clearly see that C of AB closure is not equal to C of AB, and so it is not closed in LP of AB, and hence it is not Banach. Next we have the same space as a subspace of B of AB, that is C of AB as a subspace of B of AB with subnorm is Banach. Okay, so we have considered the space as a subspace of LP of AB, but it is not Banach there, but here as a subspace of B of AB with subnorm is Banach. Okay, we will see the proof. We have C of AB is equal to set of all x element of B of AB where x is continuous on AB, that is the space of all bounded continuous functions on AB. Okay, we have to show that this is a Banach space with the subnorm. For that, consider a Cauchy sequence xn in C of AB. Then this means that norm infinity of xn minus xm is less than epsilon for all n and m greater than or equal to n naught, means supremum over all t of all mod xn of t minus xm of t is less than epsilon for all n m greater than or equal to n naught. Supremum is less than epsilon means each member is less than epsilon, and hence we have sequence xn of t is a Cauchy sequence in K for every t element of AB, and since K is complete, we can say that sequence xn of t, we can say that sequence xn of t converges to x of t, and so sequence xn converges to x uniformly on closed interval AB. Okay, and we know that sequence xn is an element of is a sequence of C of AB. That means all xn's are continuous bounded functions on AB, and we have found that this convergence is uniform, and so x is clearly continuous on AB, because we know that uniform limit of a sequence of continuous functions is continuous, and we have seen the proof in some example above actually. Okay, so x is continuous on AB means x is an element of C of AB, means C of AB is complete, because we have chosen a sequence xn in a Cauchy sequence xn in C of AB, and found that Cauchy sequence xn converges to a continuous function in C of AB, and so C of AB is complete, and hence It is Banach with the supno. Okay. Next we have the example C naught of T as a subspace of C of T is a Banach space. Here T is a metric space and C naught of T is equal to set of all x element of C of T such that for every epsilon greater than 0 there exists a compact set E subset of T such that modulus of x of T is less than epsilon for all T not an element of E. Okay, let xn element of C naught of T and xn converges to xn C of T. That is, we are taking a sequence xn in C naught of T such that xn converges to x in C of T. To show that it is a Banach space, we have to show that x is an element of C naught of T. Okay, so xn converges to x in C of T means norm infinity of xn minus x is less than epsilon by 2 for all n greater than or equal to some capital N. And since xn, x capital N, is an element of C naught of T, by the definition of C naught of T, we can see that there exists a compact set E of T such that mod xn of T is less than epsilon by 2 for all T not an element of E. Then modulus of x of T is equal to modulus of x of T minus xn of T plus xn of T is less than or equal to mod x of T minus xn of T plus mod xn of T, which is less than d infinity of xn comma x plus mod xn of T, and this is less than epsilon by 2 plus epsilon by 2 equal to epsilon for every T not an element of E. Means that x is an element of C naught of T and hence C naught of T is closed and hence it is a Banach space. And the next example is Cc of T is not a Banach space. Here we are considering Cc of T as a subspace of C naught of T, which is the subspace of C of T actually. Okay, we have Cc of T is equal to set of all x element of C of T such that there exists a compact set E subset of T such that x of T equal to 0 for every T not an element of E. Okay, here also T is a metric space. Let T equal to capital R. For the proof, we are choosing T equal to capital R and considering the function x of T is equal to e raised to minus mod T for T element of R. And consider the sequence of functions xn of T is equal to x of T if mod T is less than or equal to n, and 0 if mod T is greater than or equal to n plus 1, and is equal to a polynomial of degree 1 in the remaining intervals, that is the closed interval n plus 1 and in the closed interval minus n plus 1, minus of n plus 1 comma minus n. Okay, for every n equal to 1 to 3 etc. There is a rough figure of this function xn, that is it is equal to x of t, where x of t is e raised to minus mod t, and equal to 0 if mod t is greater than or equal to n plus 1, and a polynomial of degree 1, that is a line segment joining this in the intervals close interval n plus 1 and minus of n plus 1 comma minus n. Okay, it's actually a rough figure. This means that xn is continuous on capital R for every n equal to 1 to 3 etc. That means xn, we have selected actually a sequence xn from Cc of R. Okay, we have to show that Cc of R is not Banach. Okay, so we have selected a sequence xn from Cc of R. As n tends to infinity, we can clearly see that xn of t converges to x of t, because in the rough figure, as n tends to infinity, we can see that xn of t converges to x of t, because xn of t is equal to x of t if mod t is less than or equal to n. So as n tends to infinity, it is very clear that xn of t converges to x of t. This means that norm infinity of xn minus x is less than epsilon for every n greater than or equal to n naught. Okay, and this means that the limit point x is an element of C naught of R, but not an element of Cc of R. Okay, because norm infinity of xn minus x is less than epsilon for every n greater than or equal to n naught, means that x is an element of C naught of R. Okay, but x is not an element of Cc of R. So xn converges to x and x is not an element of Cc of R, means Cc of R is not closed and hence it is not Banach. Next we have the last example. P of AB under any norm is not Banach. Here P of AB is the space of all polynomial functions defined on closed interval AB. Okay, if the polynomials are considered is with a single variable, then we clearly know that it has a denumerable basis, that is a countably infinite basis, 1x, x square, x cube, etc. So by theorem 8.4 we know that for a Banach space it cannot have a denumerable basis. Okay, every Banach space cannot have a denumerable basis, but for P of AB there is a denumerable basis, and hence it cannot be Banach under any norm. Okay, so these are the examples. Hope you understand Banach spaces with examples for Banach spaces and for non-Banach spaces. Thank you.